Let's use LRFD to draw a simple shear and moment diagram for a beam that is only supporting its self-weight. So here we have a simply supported W18 by 35 at a length of 20 feet. Now, even though you're not seeing any loads drawn on this, you can actually draw a shear and moment diagram based purely off the self-weight of the beam, and that's what we're going to do here. So since I said we're using LRFD, we can use combination 1 to figure out what our factored load is going to be, which is going to be 1.4 times the dead load, which is this 35 feet, because the self-weight of the beam is considered to be a dead load. We can figure out what our factored load is going to be, or our factored distributed load, which we're going to call W sub U. This is going to be 1.4 times 35 PLF, which is 49 pounds per linear foot. Now, we have to take this information and do a few things with it. First off, our pounds per linear foot really isn't going to do too much for us here in this specific case, because we are dealing with the end reactions, and we need to figure out what those end reactions are. And the linear weight by itself doesn't really help us. So if we take this, we can turn it into the weight of the beam because we have 20 feet. The beam's weight can be considered to be uniformly distributed because at any point along this, we should have that 35 or factored 49 pounds per linear foot. And this is a uniform distributed load, meaning our end reaction is just going to be the beam weight divided by 2, making this calculation really easy. If we look at what our end reactions are, since it's a simply supported beam, we can argue that there is a force here, but there's no force acting in that direction, so you can probably assume that FAX is going to equal 0. Not probably assume, you can assume that. And then, as I mentioned, FAY and FBY are going to be equal. They're just going to be half the weight of the beam. The weight of the beam is 49 pounds per linear foot times 20 feet, which is 980 pounds or 0.98 kips, which is slightly more useful for what we're doing in this application. Almost everything is going to be done in kips. So FAY equals FBY, which is 0.49 kips. We can go down and we can draw this shear, We can go down and draw this shear moment diagram. It's going to start negative and go positive. So it's going to quite simply be this, because we just have one uniform distributed load. And this is going to be 0.49 here. This is going to be, this is negative 0.49 here, and this is 0.49 up here. Pretty simple for this case. Now, when we are dealing with this, we can turn this into a very simple parabola when we're looking at the moment diagram. And there's a couple of other ways that you can consider going about this, but this is the normal way I like going about it. We know we're going to start from 0. In this case, we have equal and opposite areas on this side. So what we're going to be dealing with is a positive parabola that is going to terminate at 0 because those end reactions are equal, so it's going to come back. I have this slightly misaligned here. Let me draw this here. So this is going to be our peak. 10 feet, which is where the shear diagram crosses the x-axis, is going to be the peak of our parabola, and this function is increasing. You can do linear interpolation to figure out what this equation would be, figure y equals mx plus b to get the value at any point along this for, if you take y equals mx plus b and then integrate for the shear diagram, if you integrate the shear diagram, you will get the moment diagram. But since we know we start from 0 because this is a simply supported beam, we can also just calculate these areas here and they'll tell us everything that we need to know, which is my favorite method of doing this. So 0.5 times 0.49 times 10 comes out to be 2.45 kip feet. We can take that and we now know that this point here is going to be 2.45 kip feet. And then we know the shape of the graph just based off of what would happen if we integrate a linear function. That's what will happen. Now, another way that you can commonly go about dealing with a distributed load is you can look at a common equation for a distributed load, and your moment max, which is going to correspond to this point here, is equal to 1/8 of your load, or yes, your distributed load times your length squared. So if we do that, we have 0.125, which is that 1/8. We're doing kip feet here, so our distributed load is 0.049 kips per linear foot, because it's 49 pounds, and if you do that distribution, that's where it comes out, times 20 squared. If we do this math, we have 0.125. 0.125 times 0.049 times 20 squared also equals 2.45. So you can see these methods check out against each other. So this is just a very simple shear moment diagram. It's a good thing to check up on your fundamentals. And if you were to do the same thing with any sort of distributed load being applied to the beam, you would follow the exact same process. You would have a slightly different looking shear and moment diagram if you had point loads as opposed to uniform loads, and we will go over those in a different video. But I hope you guys found this helpful, and if you did, please like the video and subscribe so you can find more content like this. Thank you.